Hello everyone, my name is Hillary, and today I'm going to show you guys the monotone convergence theorem. Firstly, I wanted to give you a brief introduction of what I'm going to talk about in this presentation. There are three parts. Firstly, we're going to know what is a monotone sequence. Next thing is what is a bonded sequence and how to prove its bondedness. And the last thing is going to formally prove the monotone convergence theorem. So from the definition, that a monotone convergence theorem says that if a sequence is monotone and bonded, then it converges. So the first question is, what is a monotone sequence? From the definition of the book Understanding Analysis, we will know that the definition says a sequence an is increasing if an less than or equal to an plus 1 for all n belongs to a natural number, and decreasing if an bigger than or equal to an plus 1 for all n belongs to a natural number. So basically what this definition is saying is that if a sequence is either increasing or decreasing, it is a monotone sequence. So the next thing we're going to do is we're going to know if a sequence is increasing and bounded above. If we know that a sequence increasing and bounded above, we will prove it's converged. So notice here we're only giving example of increasing and bounded above is because the ways to prove a sequence is decreasing and bounded below is going to be the similar. So how do we know the sequence is bounded? This is the first question. From the definition, it says a sequence Xn is bounded if there exists a number m bigger than 0, such that the absolute value of Xn is smaller than or equal to m for all n belongs to the natural number. So which means we're going to find an interval negative m to m that contains all of the elements in the sequence of Xn. So here I'm going to present my iPad and show you guys how I do this proof. The first thing we're going to do is we wanted to assume Xn converges to a limit L, which means if we are given in a particular value, let's say epsilon equals to 1, there exists n belongs to a natural number such that if smaller n bigger than or equal to the big N, then Xn, we know that it is in the interval of L minus 1 to L plus 1. Because we don't know if L is a positive number or negative number, so we can conclude that the absolute value of Xn less than absolute value of L plus 1 for all n bigger than or equal to the big N. To be more visualized, I wanted to draw a graph here. So all of the dots you can see are x, like a element in Xn, and we take an interval L minus 1 to L plus 1. In the middle is L. And in this interval is obviously Xn and m smaller n bigger than or equal to the big N. Notice here we wanted to state the statement that we wanted to have this m equals to the maximum of all of the n, of all of the numbers in Xn. So in the graph you can see we can have this capital M here. So it will follow that the absolute value of Xn smaller than or equal to the capital M for all n belongs to the natural number. In this case, we finish our proof of the bondedness. As we prove that the sequence is bonded, here we're going to prove the formal proof of monotone convergence theorem to show a sequence is monotone and bonded, then it converge. First of all, let an be monotone and bonded. So to prove an converges, we will using the definition of convergence. And we are going to need an L here to be our limit. So let's assume the sequence is increasing, which notice here the decreasing case is going to be the similar. And we're also going to think of the set of points an, which n belongs to the natural number. So by assumption, the set is bounded. So S equals to the supreme of the sequence an and belongs to the natural number. We'll get an obvious claim here that limit an is equal to S. But we also have to prove for this claim. To prove this, we will let epsilon bigger than 0. So because S is the least upper bound for the sequence an and belongs to the natural number, so S minus epsilon is not an upper bound because epsilon is bigger than 0. So there exists a point a bigger n. Notice here a bigger n is a number instead of a small n is a sequence. So we'll have epsilon minus s minus epsilon less than a big N. So because an is increasing, which means that if n bigger than or equal to the big N, we will have a big N smaller than or equal to a small n. So we'll get the inequality that s minus epsilon less than a big N less than or equal to a n less than or equal to s less than s plus epsilon. So a big N less than s plus epsilon. Because we don't know s is positive or not, we will have absolute value of a big N less than minus s less than epsilon. Because epsilon is bigger than 0, in this case, we finish our proof of monotone convergence theorem. As a conclusion, the monotone convergence theorem is very useful in the study of infinite series because as the way we're proving it, we didn't explicitly mention the actual limit. So it would be really helpful if we have a really large series and we can still prove the convergence of the sequence. Another thing is very useful in doing the preliminary investigation in mathematics to formalize the relationship between sequences and series. This is my citation, and thank you very much for listening to my presentation.